Okay, thanks. Yeah, thanks a lot for having me here once again. And yeah, good to be talking about this in person. I hope the voice and everything is fine with the online audience as well. Um, yeah. Okay. So yeah, I decided to talk about this endpoint contribution. My pointer will be here. Because this is something we have been thinking about for some time, and we kind of find that it has a lot of scope and opportunities for future work. So we are kind of excited about this program, and hopefully I'll be able to convey to you some of the things that we have found, and you'll probably see that we have more questions than we have answers, but let's see. Yeah, so it is based on these two papers and ongoing work with Dan, Gilad, and Fook. So yeah, many ideas, of course. I mean, this talk will be mostly based on field theory, entanglement, and so on. And some of the key players of this talk will be subregion density matrices, rho A, the corresponding modular Hamiltonians defined in this manner, minus log rho A. So it's like if you have some subregion A bar, so you have some Hilbert space, some pure state psi, and you have bipartitioned the Hilbert space in A and A bar, then you can define these quantities. And in fact, I'll talk about rho A bar, H A bar, but I'll also be talking about extended modular Hamiltonian, which I'll denote by this H with a double arrow here, and which is defined like this. And the basic goal of this talk will be to compute modular Hamiltonian HA corresponding to a density matrix rho A for the subregion A for an excited state. And the excited state will be obtained by perturbing the vacuum state by some unitary operator. Unitary operator excited state in a moment. So this is the state. We have some unitary operator acting on the vacuum state. The unitary operator looks like this. So G is some Hermitian operator given by some Hermitian operator O of X integrated over some Cauchy slice, or some, in this case, we'll take some space like on null hypersurface. Okay, I will have some pictures in a moment, but basically, the situation will be that I have some, let's say, some t equal to 0 slice here, some, this is, let's say, the x direction. So, so you have some region here. Vacuum state the modular Hamiltonian corresponding to A region HA. Then for the perturbation with U, the H will shift because the density matrices are changing. And in fact, there is also this parameter epsilon here, which will give us the order of perturbation. So we'll do the whole calculation at first order in epsilon. To some cases, we can actually go to higher order, in fact, even exact results, but more generally, I'll only talk about the first order perturbation. And so the related change of HA is what I'm denoting by delta HA. Okay, and then you can also compute delta HA bar, and from there you can compute delta H with this upper upper left right arrow thing, the full delta H. And we believe that so in CHEP-th, whenever we talk about that, I have bipartitioned the region into A and A bar, we are actually being a bit imprecise. We actually cannot do that. It can only be done in a finite dimensional system. And we'll see that this kind of non-factorizability of Hilbert space will show up in a very interesting way in this delta HA or delta H. And we'll provide a general form of delta HA for perturbations by Jn. So this O operator here, this could be any operator J. In this case, we will mostly be dealing with primaries with some what we call a modular weight n. So what is modular weight n? It's that when this operator Jn, or in this case O, which is Jn, when it transforms under modular flow, so this is the modular transformation, this middle line here, then if it has modular weight n, then for Rindler subregion, if the modular Hamiltonians correspond to Rindler, corresponding to the Rindler subregion, then it transforms in this fashion. Sorry. Escape, no? Yeah. So basically, as long as we are looking at Rindler subregions, then you can very easily think of n as some sort of difference between the plus indices and minus indices that you have in J.
So this S0 is
vacuum, yes. So yeah, whenever we are talking about,
this is kind of like you're organizing the operators in
exactly, precisely. You can call it boost weight for this case. And a good amount of literature actually studied similar problems and vacuum. You can have n fractional. We haven't studied that. That's a good question. Yeah. I mean, frankly speaking, I have not seen the definition of modular weight for general bipartition case, but only for Rindler. Okay, so that I should tell you. There is another paper by Liukovic and Parikar, which actually came before us, and they talked about modular weights, but that's also in Rindler. Yeah, so as you can see, I mean, for a long time, people have been calculating this excited state modular Hamiltonians, but most of their expressions are quite actually formal and abstract. And we will be using certain expression coming from one of these papers, for example, this paper by Sarosi and Ugajin. And what is missing in those papers is that they don't distinguish between the origins of various contributions in delta H, which I'll show you that that's where the surprises lie. And also, most of them talked about stress tensor perturbation, and we will be doing some arbitrary n perturbation. And in fact, people also talked about modular Hamiltonians under shape deformation. So what they had in mind in these papers, that you have some subregion and you deform the subregion a little bit. So what is the corresponding change in the modular Hamiltonian? And actually, there is one paper, this paper by Faulkner et al. Well, so they had a series of papers. So it's one of the papers where they actually found a result which is very similar to what we have. Okay, so any questions so far?
Non-factorizability of the network space.
Yes, yes, yes. So yeah, so you can think of it as so when you have a finite dimensional system, only then you can divide your sub-region into A and A bar subregions, and only then rho A or HA, these make sense. But in general, in field theory, if you take a state which is HA acting on some state psi, then you can show that that state has a divergent norm. So it's not a well-defined operator. But so what you should do in modular theory, if you have field theory, is that you should work with modular operators, which come in the Tomita definition of Tomita operator S. And that modular operator delta, I'll have it in the talk. It's just an operator in itself, and if you specialize to a finite dimensional system, then that delta can be written as rho A tensor rho A bar inverse. And this delta minus log of delta is this H uppercase, this full modular Hamiltonian. And only when you specialize to finite dimensional case, this H is HA minus HF.
So but the double arrow thing is well defined in the quant.
In quantum. Okay, any other questions? So this is our setup. This is kind of the earlier work. And then now I will briefly discuss our results. And then I will discuss one example where we can readily see that we get our results in a different way. And then I'll discuss how to generally derive our results. And then I'll discuss open problems. Okay, so naively, if you have this some pattern some A union A bar, so you can think of, I mean, even if it is some arbitrary spatial slice, you can think of this part of the perturbation is what corresponds to this A bar region, and this part of the perturbation corresponds to the A region. So if you naively think in that fashion, that okay, let's say this is from some minus b to 0, x equal to 0, and to some x equal to a, then this perturbation corresponds to A bar, this perturbation corresponds to A, then this will imply that this G, remember the G was U was e to the minus epsilon G, and U was the unitary operator with which you perturb the vacuum. So this G will then be written as some GA plus GA bar. So I have some part of GA and some part of GA bar. And now since GA and GA bar commute because of, I have taken this space like slide, it would seem that the unitary transformation factors into this U equals to UA tensor UA bar. You just exponentiate. And then you can show that the reduced density matrices. So if I still am adamant and want to define some rho A and rho A bar and so on, then these reduced density matrices, modular operators, modular Hamiltonians in the excited state psi will behave simply by this unitary transformation. So rho A will be rho A0, which is the rho A corresponding to the vacuum state, and it will just be U rho A0 U dagger, U a dagger, and similarly for rho A bar. And then when you define the modular operator delta, which is by definition this for finite dimensional system, then it will be some U delta 0 U dagger, where delta 0 is the modular operator for the vacuum state, and similarly for the extended H. And then you would think that to first order in epsilon, the change in H is just this commutator term, minus epsilon G comma H 0. But this is only true for discrete systems, and as we'll see that if you are very careful in dealing with field theory correlators and so on, there is an explicit endpoint contribution that arises. And what I mean by endpoint I mean the point where these two subregions are separated. So heuristically, you can think of it as that when I define G like this, GA plus GA bar, I did not exactly know, or there is an ambiguity to place the perturbation that is sitting here. I don't know where to put it, whether it should go in A or it should go in A bar. So if it were, for example, a lattice system, then this ambiguity will not arise. So this is what we will see an endpoint call an endpoint contribution, which is an addition to this commutator contribution, which seems to be the meaningful result for an excited state to first order. And the result is the following. We'll see that if you perturb the state by some operator which has modular weight at the -1, 0, or +1, there is actually no contribution, such endpoint contribution. It just is the commutator piece. But however, if you have some, perturbation by n equals to 2, 3, 4, and so on. So n equals to 2, you can think of as a stress tensor perturbation. And n equal to 3, 4, and so on. Then this endpoint contribution. So there is always a commutator contribution, which will be I epsilon G comma H0. Plus there is this piece, which what we will call light ray moment, and because it is light ray moment. So let me explain. So you have, suppose, perturb the state with some operator Jn, okay, along some space-like slice. So the endpoint contribution becomes, so there is a sum, as you can see, over K and over L. The L sum depends on N and K, the K sum depends on N. And then you see, so for L equal to 0, it's like you take the operator with which you perturb Jn, and you have integrated it over the x plus horizon. Okay. So it is like, this is one of the endpoint contribution, and this is called light ray operator in conformal field theory. And then, but if you, because n is, so for n is 2, actually this is the only contribution, this light ray operator. But if n is higher than 2, then you also have this x plus to the some power and the descendants of Jn. Okay, so this is why we are calling this whole contribution as light ray moments. And there is a similar contribution if n is -2, -3, -4, and so on. And as I said, if it is simply n equal to 2, or for example, which is the relevant case for stress tensor perturbation, then you can show that this delta H endpoint boils down to NX operator. This delta H endpoint is, you see, there is a, this is the full modular Hamiltonian change. So this is an NX operator, but if we calculate it for delta HA and delta HA bar, this will be half NX operator. So it will be integration from 0 to infinity for delta HA and 0 to -infinity for delta HA. I'll explain that in a moment. Okay, so yeah. So theta is this angle. Yes, yes, it was somewhere before. Yeah, so thanks. This f0 means the value of the function f at 0.0, but fk0 is the kth derivative of the function evaluated at x. Exactly. Yeah. So in fact, if it is stress tensor perturbation, then k just takes the value 0, so it doesn't depend on the derivatives of f. But otherwise, there are all these derivatives that happen. Then it will be equivalent.
Somehow it seems to be naturally defined along with.
Right, right. Actually, we'll see that without going through any technicalities, you can simply show that the endpoint contribution, whatever it is, it has to satisfy certain conditions. And so it is very important that it is an operator integrated along null ray, because only then it satisfies those conditions. Okay. Any further questions? Okay. So yeah, so let's first try to convince ourselves that at least we have the correct result for the stress tensor perturbation, and it is actually very easy to derive, because there, if you change the state by state stress tensor perturbation, it is equivalent to doing a local conformal transformation. So in this case, in fact, if you take CHEP-th, it is very easy to do, even for, you can even do it for any finite subregion. So it doesn't have to be A, and A bar doesn't have to be Rindler. It can be A, could be some UV region, and A bar is the rest. Because for this region, I can, for UV region, I can precisely write down this extended modular Hamiltonian for vacuum state, and that looks like this. So Z is the light cone coordinate, x plus. And then if you do a conformal transformation, Z to G of Z, then this H UV. That's right. Well, yeah. That's right. But ultimately, this integral is, I mean, the modular Hamiltonian. So, so under the action of this conformal transformation, it's very easy to show that, you know, U goes to G of U, V goes to G of V. The stress tensor transforms in a certain way, and it gives this form. And then if we want to match with our, you know, this general result, which, yeah, but that actually just give a classical number. You can show. No. Yeah.
When you're a delta, it's like this commutator is basically
H naught. Mm-hmm.
So I think that that would mean that the extra piece is a constant.
Yeah, and also it does not contribute to endpoint contribution. You could have contributed to endpoint, right? Meaning if it were endpoint. Yeah, sorry, endpoint.
No, yeah, so you mean like the extra piece in that?
Yeah.
Yeah, but that extra piece, I'm assuming that if you want to do it sort of calculationally, you will have to do it by somehow extracting a piece from the. You do the calculation, I think that's what you would do.
Yeah, I think equivalently, I can say that I can just absorb that extra piece as a kind of constant shift to H, and when I compute the commutator, it doesn't matter. Yeah. So, you know, to match with the general results that we had for at order epsilon, we have to realize that if we choose G of Z as Z plus epsilon F of Z, then actually the corresponding change of state is precisely what you had when you had this unitary operator U equal to first order in epsilon 1 minus I epsilon G acting on the vacuum state, because having this perturbation will correspond to some unitary some conformal charge Q, which to first order will be explicitly e to the IQ, which will give you the change of state, will actually be this U to first order in epsilon. So to match with our previous results, the point is that this conformal transformation you can expand to the first order in epsilon with some F of Z, which will precisely relate to the F of Z we had before. And yeah, this will correspond to the generator FZ T plus plus Z. So if you, so all I now have to do is to write this down to first order in epsilon, and there we did that. So the epsilon to the 0 piece will be precisely HUV0. So if I subtract that to find the delta, the change part, which is order epsilon, then this is the form. And then you see that I have written it in 2 lines because the first line is the commutator contribution. This you can check explicitly by using TT commutator, because G has a T inside. In H0's definition, there is a T inside. So you can compute this explicitly and you can show that it's the first line. And the second line, you see it becomes 0 if f of u and f of v are 0. So if the perturbation is absent at the endpoint, so that's why it is endpoint contribution, and this is precisely the leftover part from the commutator contribution.
So this is true only for conformal field theories, and that's why you are able to do it for u, comma.
Yes, in 2D I can do it by doing this conformal transformation, so it's easy. Otherwise you are doing it for half. Yeah. And then we are adding delta HA minus delta HA part to get the delta H. So as I said, the second line is an endpoint contribution because it vanishes if u equal to f equal to 0, and that is precisely the non-commutator piece. And you can actually figure that out, how much is that for in this fashion. So you take f of z. It's not necessary, but it doesn't matter in this case, to be some constant function across the endpoint. So this point here is x equal to 0. And I have taken this f to be some constant across minus b to a. B and a are positive numbers. Then you can write down this expression here. It becomes that, and also have taken u equal to 0 and v to infinity. So now I'm really trying to extract out the endpoint effect for Rindler. Okay, so I could have also done it for uv sub Betian, but just to make contact with the previous case, I'm taking u equal to 0 and v to infinity. And then now if you take a and b to 0, so naively you could have thought that, okay, if I put a and b to 0 to begin with, then there is no perturbation across the endpoint. Okay. And then maybe the whole thing will be 0. But once you do the conformal transformation first, keep a and b finite, and then put a and b to 0, then you will find out that there is some piece left over. And this is precisely the piece that you will get from our general expression when you put n equal to 2. So this is the NA operator appearing here. Yeah, so there is this theta functions here, and then you have to take some, I believe, some derivatives here. So if you I believe it's coming from the theta function. I think if you do it carefully, I think this will come from this. It has to. This f prime piece will give you some delta functions, but I think this will have some b and a associated to it. So when you take a and b to 0, they will drop. And then these pieces will give, actually this -1 piece will give you this. Okay, so there is f prime will give you these 2 deltas, and this f of z will give you those 2 thetas, and this piece will boil down to -1, which will give you this. So it's precisely the endpoint, the second line of the previous slide, which gives you the endpoint or the NA operator. Now, this method will not work for other perturbations because you cannot always study it using conformal transformation. So we need a more general operator method. And I will briefly tell you some formulas, some abstract formulas that we'll be using over and over again. So we start by writing the vacuum state in some Schmidt decomposition form. You can calculate the corresponding. So, okay, so I should say something that, I made a huge fuss about, that you cannot actually break down your QFT into regions A and A bar, and that's why you have the endpoint contribution. But actually, we don't know how to compute it purely at the level of delta. So in all parts of our calculation, we will assume as if we have a region and an A bar region, which is of course not the best thing to do. But then we would be finding some results, but then we will be very careful in considering that operator inside a field theory correlation function. And that is what will actually give us the endpoint contribution. Okay. So yeah, so it looks a bit ad hoc if you realized it, that I made a fuss about being in QFT and not in finite dimensional system, but still my formalism works with rho A and rho A bar, but it works. Okay, and that's actually the only way we know how to attack this problem. Yes, we believe so, yes. Yes. Yeah, so in this talk, I'll not have much to talk about entanglement entropies, I mean, later on Rene entropies. But yeah, we not that I can remember. So you are asking if there is a literature that exists which shows delta H is 0 for discrete systems. Delta H is not 0 for discrete systems. The endpoint contribution is 0 for discrete systems. Yes, but there is always a commutator. Yes. So no paper actually, discussed delta H. I mean, all those papers that I showed, I referred to, they discussed delta H, but they did not differentiate between various contributions. So maybe they have talked about discrete system, maybe they have a comment in their paper, but they have not commented that, oh, but this piece is commutator and that endpoint piece is zero. And
But I think if you have a general discrete system across the system, imagine that that's not construction,
yes,
why would you expect an endpoint?
yes, of course, I agree. I agree. I agree. No. I think it is true. I'm just saying that the endpoint contribution was not discussed explicitly before, but I think it's completely.
Tautologically, the case is
Totally. Not yet. Yeah. Yes. Not yet. We have worked with relative entropies and relative modular Hamiltonians, still a work in progress. And then we try that gives you the first law of entanglement. So we still have to check that, Yes, of course. No. Yeah. No, I think what should be true is that you can show if you start with the relative modular Hamiltonian, then the first order change is 0, and the second order change being the Fisher information, it is positive. So that we still have to show. Absolutely good question. We tried. It's still ongoing. As I said, I have more questions. Yeah. I kept all those questions in my last slide. So absolutely. So one of the nice questions will be that whether there is a generalized NX type statement. And we looked at some paper on higher spin NX, higher spin version of NX. And we have to see that at least when Janes have some conserved current, then whether that boils down to. I'll mention some things along those lines. Okay. The positivity properties are also important. Let me talk about it later when the time comes. Any other questions?
This case that you're writing, you're only basically only assuming there is no assumption.
No assumption yet, yes.
Except that it is finite.
Right now, yes. But then we'll be careful in dealing with these operators. When I'll find an expression of delta H, we'll study them in a correlation function. And we'll be very careful with how the structure of that correlation function behaves as you zoom into the endpoint, as you take the near endpoint limit, and once you are careful, you can extract that. So, and actually here I would take the perturbation G to be of the form GA tensor GA bar. So the one that I took for GA plus GA bar is a special case of this, because you are considering anyway a perturbation to first order in epsilon. So if G is GA tensor GA bar, it also goes true if it's a superposition of GA tensor GA bar. So you can think of GA plus GA bar as the case when for one GA bar is identity and in the other is GA is identity. So, but anyway, this is a more general formula that we are proving. Yeah, but that is a special case of this. This is what I'm saying. So GA tensor GA bar to first order, it's whatever result I have will go through for some CI, let's say GA. And this is like special case of this.
This equation that you're writing, I completely agree. I'm just saying that the left-hand side of that equation is not the same thing as that.
Left-hand side meaning G?
No, left-hand side of that.
Yeah, it's for some special values of GA bar. And so we will, if you.
I mean, this is factorized. That does mean, the right-hand side there doesn't really factorize in the same.
No, it's a sum of two factorized forms. No, it is sum of two factorized forms. So yes, whatever formula we have for this, we'll go through for the whole sum.
Yeah. If it goes through for the left, I agree that it will go.
Yeah, it will, because it's first order in epsilon. So they will simply add up. There is no cross terms in the product. In the second order, you have to be more careful. Then there will be some cross terms coming from endpoint contribution and the commutator piece to second order in epsilon square. Okay, so then you have to be more careful. And we will use this expression that we get from here and apply it to this case. So it will.
That's what I'm worried about. I mean, if you're using it for the left-hand side of that expression, I think I can understand.
No, for first order you can do it. And we will actually derive everything. So yeah, so I will be very fast here because some technicalities. So you can calculate now delta rho A, because this perturbation G is what will now give rise to this psi, and then you can calculate some delta rho A corresponding to the state psi. And well, so it readily generalizes to some rules. And then well, so then you can, so you have this GA and you have this GA bar. So GA, remember, is some perturbation here, GA bar is some perturbation here. And then to simplify the situation, you can define modular conjugated operator GA bar tilde, which is defined by this. GA bar tilde is J, GA bar J, where J is what appears in Tomita theory. So in Tomita theory, I don't want to get into the detail of this. There is an operator, antilinear operator S, which has a unique decomposition J delta to the half, and this is the Tomita, the modular conjugation operator. For Rindler, it becomes CPT. Okay, so this is actually one of the reasons why things simplify for Rindler. And it has also the property that in modular theory, if now you specialize to finite dimensional system, then this GA bar tilde has the property that it interchanges the basis in this fashion. So I GA bar tilde J or I J GA bar J J becomes J GA bar I. Okay, this is the property of capital J. So if you use that, then the delta rho A expression becomes this. The rho expression becomes this. And one thing that you can that happens is that if GA bar is an operator corresponding to the A bar region, then after this CPT conjugation, you get an operator which is in the A region. Okay. So now we have written everything in terms of GA and GA bar tilde, both of which are operators living in the A region. Okay. And as you can see, if you look at this delta rho A a bit carefully, this is not, so this delta rho A should have been, if it were a finite dimensional system, it should have been G comma rho A 0, but it's not because of this GA bar tilde. It's still a commutator. Actually, you can still write in a commutator form, but it's actually not this. And this already gives us a hint of the fact that maybe there will be other contributions. And then we borrow a formula from Sarojugajin's paper, which basically is an expansion of logarithm. So they had used the primary definition of HA. So HA is minus log rho. And then you expand both sides in epsilon. And to first order, for example, you can write that HA0 minus, HA minus HA0, it basically becomes this the second term here.
The middle expression that is written there is also the matrix, the matrix version of
yes.
the main element.
Yes. So in this expression, you have, so this is your delta H. So this delta H is basically some sort of transformation. It's not actually modular transformation, but some sort of transformation of this delta rho A piece. So once you know delta rho A, because you know how you changed your state, you can plug that in here. You can compute or hope to compute this expression explicitly, which actually nobody did before somehow, and you can then hope to compute delta H. So we have this expression of delta rho A, and we will just substitute it here. And well, you do some algebra, you define the modular float operator O at some modular parameter value S. Remember, whenever I define a modular flow of an operator, it was defined like e to the minus IH0 S O at S equal to 0 e to the IH0 S. So this is the modular parameter. So for how long you have flowed it by modular Hamiltonian. So this is the definition here. When I have, okay, H0 is like my double-sided full modular Hamiltonian. And then in terms of this S, you can simplify this Sarojugajin formula and basically it takes this form. So what I have to do, I have to identify what is GA, what is GA bar tilde, which is the modular conjugated GA. I have to flow them up to some S. Some S could be imaginary, some of the S's, and then I have to integrate S with that, 1 over 1 plus cos hyperbolic S factor. And I would now like to very quickly redo the stress tensor perturbation case using this formula. But actually, I will also skip something because of time and because we'll anyway do it properly in a moment. I have to like sharply finish at 4. Okay. All right. So yeah. So if I now specialize to the stress tensor perturbation case and the Rindler subregion case, So yeah, so Rindler, so A means x greater than 0 and A bar is x less than 0. And G is, some minus B to A fx t plus plus x dx. Then I can divide this G into 3 parts. One is, so here actually I have taken even minus infinity to infinity. It doesn't matter because as long as, we are focusing on endpoint contribution, I will just, this part is what is relevant across some region in across this endpoint. But otherwise, the perturbation can be all over the space. I don't care. So yeah, so this is my G in this case, and I have divided it into 3 parts. So minus infinity to minus B is only in the A bar region, and this A to infinity part is only in the A region, and this the middle part is what straddles the endpoint. So let's work with the first part, and I can just work individually with all the parts because it's first order in epsilon result. Okay, so they will simply add up. So if I take the first term, then here all the perturbation is in A bar region. So GA is identity, and GA bar is this. So if I just plug it in here, it trivially goes to 0. And this is what you expect, because for a perturbation in A bar region, the modular Hamiltonian for the A region should not change, because I'm here calculating delta H A. Okay, delta H A bar will have another formula that you can find out in a method, in a similar method, and that will have the the result you want. If you take the third term, which is only in the A region and doesn't straddle the endpoint because A is non-zero, then GA is this whole thing, and GA bar is identity. And then if you plug it in here, you can do some contour deformation and this complex integral, and it gives you precisely the commutator piece, which you again expect, because now I don't have any problem with the endpoint because endpoint is irrelevant here for this perturbation from A to infinity. Endpoint is irrelevant, so the whole contribution for delta HA comes from the commutator piece. And the middle term is basically what's non-trivial. So this G is indeed should be written as GA tensor GA bar. Okay, so these are some of the steps that I will actually skip right now, if I may, because so what we have done here basically is to write this G that we have here. So let me just flash. So this G, using some formula, we will write as some t at point A times some t at point minus B. The fact that you can do that helps us to identify what is GA and what is GA bar, and then write the perturbation in G equals to GA tensor GA bar form. And once you do that, then you again put it in this Sarasugajin formula, you do some computation, and you get some result. And in all these computations, we will be careful by not just working at the operator level of delta HA, but we will actually, for clarity, will consider it inside some correlation function. Okay, and you will get the result that you want to obtain. Now, why I am skipping this? Let me tell you that I'm skipping this because writing a G like this. So remember this formula that I have from Sarasugajin, I derived it for G equal to GA tensor GA bar. And what I'm doing here is I'm writing G equal to minus B to A, t plus plus x f of x, as if it is some GA tensor GA bar. I have to identify this GA and GA bar and plug it in Sarasugajin to find it. But doing it for higher modular waves will become difficult. So I am anyway going to show you formalism where I would write G as GA plus GA bar. And then I will apply that in Sarasugajin and do the whole thing. because it's just technically difficult, okay, for higher modular weights. So this is why I'm skipping, because similar technicalities will also appear here. And this we could do it after some sweat for stress tensor perturbation and scalar, but in this case we will be able to do it for all modular with, sorry, yeah, with identity and identity. But the thing is, the thing to note from here is that even if you write GA in this form, which is, as I said, is a bit difficult to write for modular, higher modular weights, ultimately when you put it in the Saros-Yugajin formula, you get delta H at Ty to be something from which you can, so T of Y is some spectator probe operator. So Y is, you know, some faraway operator initially, but it can be anywhere. You can move it around and you can strip it off from this expression, and you can just look at what is delta HA, and it becomes the commutator contribution plus this endpoint contribution. And if you actually now go back, write down delta HA as commutator plus the endpoint contribution and take a correlation function with T of Y, you can find that this is the answer. So you can do it. Okay, so now I would do, and also stress tensor perturbation is basically, you know, null perturbation in 2 dimensions. But now I will do the most general JN perturbation acting over some space-like slice with some non-zero theta. Okay, and the perturbation will look like this. This is just technically easier. Okay, any question? I went through the stress tensor derivation for the important piece a bit too quickly, but anyway, if you have any questions, let me know. Okay, if not, then let me straight away go to this, because the process is almost the same. It's just that I no longer write G as GA tensor GA bar, but I write G as this. But ultimately, whatever my GA and GA bar is, now it's a bit easy to write down. What is GA and GA bar? I'll have it here. This is GA and GA bar. Now I can easily put it in Saros-Yugajin, and again I will write down some delta HA. I will consider the delta HA with some probe operator. I'll have a correlation function. Then I'll be able to do this S integral. Okay, that appears in Saros-Yugajin. So this is why this is easier, because you see this is a perturbation going from, let's say, some minus B to A, which has some part on the left side, some part which straddles the endpoint, and some part on the right side. And I have simply defined my GA to be from minus B to 0. And I have simply defined my, that's my GA bar, and I simply define my GA as 0 to A. So that is very easy to do. You do not have to always depend on some sum rule, which I just showed you, which is very difficult to derive, to write it in this form. So it's easier to just define GA and GA bar this way for any perturbation and identify GA as 0 to A of this integral and GA bar as minus B to 0 of this integral. So at least the setup is much simpler now. And then we would again put it in Saros-Yugajin formula. And the Saros-Yugajin formula that we had here, this formula on top. So what I would do is, once I will take GA bar to be identity, and then I will write a plus with a part where GA is identity. And that would be my full answer for delta H. Okay, to first order in epsilon. And that formula becomes this. This is the first line. So if you write it as sum of 2 terms, then it will be some GA at S minus I pi GA bar tilde at S minus GA at X plus I pi GA bar tilde at S. And here we have used a different variable in the second line, W is e to the minus S. Okay. Some comments. Okay, questions about how I derived this, right? So the idea is clear. Once again, I did the Schmidt decomposition. calculated delta rho, used Sarasugajin for delta rho. I achieved that formula some slides ago, and then I wrote G equals to this way, and that gives me this. Now, some comments is that these two pieces seem to be canceling out. Okay, but you would see that if you actually cancel it out and write it as GAS minus I pi minus GAS plus I pi, forgetting about these two pieces, then this integral is not well behaved at S going to plus infinity and S going to minus infinity. However, if you trivially add these pieces here and here, then they have a very nice behavior at S equal to plus minus infinity, which is W equal to 0 and infinity. And this again we take to be the signature of the fact that you cannot really write down the Sarasugajin formula by completely forgetting about this GA bar tilde part. So this, when I say this is divergent at S equal to plus minus infinity, I mean when you consider delta H with another probe operator and consider the correlation function in the field theory. So you actually need those two parts. I wrote it in blue. They cancel out, but we will consider them always. We have another cutoff here. So yeah.
To actually arise from that formula that you wrote down.
But they cancel out.
But they cancel out. So you're just emphasizing that you're not canceling them out.
I am not canceling them out yet, and in fact, if I cancel them out, I will run into trouble. I will see the behavior. So for now, I have kept cutoff at W equal to 0 and infinity, but I would not need it if I have this regularized part. Okay. And I have also introduced this for technical reasons. So I have S minus I pi. If you look at the Sarasugajin formula, so you have a modular flow by an imaginary. Yes. Yes.
Cutoff that is taking.
Yes. 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 So for technical reasons, this imaginary modular flow will also regularize in this fashion. So it will go till S minus IR, then we will take R from 0 to pi. And when we will study this delta HA with another probe operator in a correlation function in field theory, as we take R from 0 to pi, we will then be able to keep track of how the poles and the branch cuts rotate, and ultimately what is the the S integrals contour prescription. And this is what I just said, that if you take GS plus minus I pi plus GA bar tilde S, only then it has the behavior as R goes to pi, it has the behavior that as W goes to infinity, it falls off, and also as W goes to 0, it falls off. And this fall off behavior is independent of N. And that will actually help us in a bit when I'll draw the contours. That will actually help us to close the contours at 0 and at infinity. Oh, delta is the conformal dimension of J. Yes, 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 yes. So if it were, integer numbers, we'll have poles, and if it has, we'll generally have deal with branch.
Value y, which is initially far separated, but as you move it around, it can develop some
singularities in the correlation function. So you will have to basically deal with such correlation functions once you deal with this Sarasugajin formula, this version of Sarasugajin formula delta H A J N Y. Okay. So you will have correlation functions of this form that you have to deal with. And now all you have to do is to write down these correlation functions, keep track of the contours and how the branch cuts move, and for various choices of GA and GA bar, you can then compute delta H, and then you can hope to extract out delta HA from the delta HA J and Y correlation function. So that's basically the plan. Okay. And the branch cuts actually in the W plane, we are doing everything in W parameter space. Yes, yes, yes.
So, but there we kind of know the 3-point function.
Yes.
But here the 3-point function will bring in the CIJ case.
3-point functions, I don't have any 3-point functions anymore because now I have not written in terms of G at n such G bar.
That's also
Helpful. Yes, that's true. So the branch cuts will actually look like, the branch cuts will be weirdly placed for some general value of R. But as R goes to pi, which is finally the answer we want to get to, because this is what ultimately R goes to pi, then the location of the branch cuts will be like this generically. So you will have one pole at -1 in the W plane coming from the 1 plus 1 divided by 1 plus cos hyperbolic S term. And then there will be some theta, B, and A dependent branch cuts. And remember W contour that goes from 0 to infinity. And if you keep track of the rotation of the cuts properly, then it will actually, the contour will look like this. So basically, yeah, delta H J and Y will be of this form. And then once again, I'll very quickly show you that I get at least some meaningful results when I have perturbations purely in the A region or purely in the A bar region. So for example, if the perturbation is purely in the A region here, so yeah, minus B and A both are positive, then you have a situation like this. So all those branch cuts are now on this location, because this diagram I drew when B is positive and A is positive, but this diagram I'm drawing when minus B is positive. So everything is on this side. Anyway, but because we have kept in the Saraswati-Gaussian formula those G bar tilde pieces, I can close the contour here, I can close the contour here, and what it ultimately becomes, you can deform the contour and you can only enclose the pole at -1. W,
the 1 by W.
actually they come from this correlation function right here. So you have, you see, here.
Yeah, but that's power is basically going to that, I think.
Yes.
That's what this is general, but if it is an integer or something, it won't get that.
Yeah. Yeah, I think in this correlation function you have something like delta plus n by 2 or something. Yeah, and delta minus n by 2 as power.
But I'm just wondering, like, this is so there's some assumption about the generosity of delta, so that you can assume that they're right.
Yes, if they were integers, because n is also integer, they will be poles. So in this case, it will be just picking up the residue at -1, and you would get the commutator piece. It's very easy to show, and it's even easier to show that if the perturbation is purely in the A bar region, so all the cuts are on the left side, you can still close the contour here, and nothing contributes, and you get 0. And these two results you can right away expect, because as we said before, also for the stress tensor perturbation case in this method, was that if the perturbation are purely in terms of A region and does not touch the endpoint, then it is purely commutator piece. And if it is purely in the A bar region, then delta H should not see that. So it should be 0. And then, you have a situation when the perturbation straddles the endpoint. It's a bit, technically subtle, but maybe you don't have to worry about it too much. The point being that, we have written the delta HA as some dx plus integral fx plus ix plus, where ix plus is given by that. It's just a rewriting of the Sarasugajin formula. And once again, we have calculated delta H J and Y, which for ix plus J and Y gives this form. And then you can write down their branch cuts in this fashion in W plane. I'm being intentionally a bit fast here.
But small x and large x, and we will see that for
large W, even for small x, and definitely for large x, the behavior of these correlation functions, they kind of die off. That when you have small w but small x, then there is a divergence which goes as 1 over w to the n. Okay, so in general, you will have no problem in this case closing this contour, which went like this left u. And in this case, you will have no problem closing the contour at infinity in the W plane. However, there will be problems at x plus equal to 0. And you can do some numerical analysis to show that this ix plus jn y, this correlation function at x plus equal to 0 has various delta functions as its divergence, delta functions and their derivatives. So I have not shown the numerical plots, but you can show them. It's in the paper. We have tried to find the coefficients of those delta functions. These are what will give rise to the, in the delta HA, the light ray moment. So to extract their coefficients, we studied this x plus to the k, ix plus j and y, and you know, yeah, if you do the computation near x plus equal to 0, then you can find out that essentially, you know, the result looks like this. So you get some for x plus equal to 0, you have to
x plus
some derivatives of delta functions and some quantity which is nothing but this light ray moment, which will eventually obtain in delta H. So I again skipped some steps, but you know, it basically goes exactly like the other cases. It's just that you have to be careful with the x plus going to 0 limit, and you have to also expand in x plus equal to 0 to extract out the subleading singularities in these correlation functions. And then if you compute x plus to the k, I mean these correlation functions with x plus to the k, then you can extract out these coefficients that you have in the I, the integrand. Okay. So I don't want to get too much into the details of it, if that's okay. Or if you have any questions, I can slowly go through this part. Okay. Anyway, putting everything together, the result of you know, this I, which was this, I was this quantity, you know, this will become, this will have some commutator piece and this will have some endpoint piece. So what is our so basically there is a commutator piece. We are looking at x plus going to 0 case, but remember, so our perturbation is like this, and we are slowly zooming in to the x plus going to 0 case. So there is some piece which is here, some piece which is here, and some piece which is here, and this piece you can show gives you, so it is like some minus alpha to beta, and we want to take alpha beta to 0. So you will see that this piece will give you 0 contribution for delta HA, and this piece will give a commutator contribution, and this piece will give you the endpoint contribution. So this is the behavior at x plus going to 0 limit. And this is what gives this I of x plus. So it has some commutator contribution and some endpoint contribution. Basically, these moments come from the fact that as you take x plus to 0 limit, there are these subleading singularities, and to extract them out, you have to do some scalar expansion. And this is basically the final result, which I also flashed before, where delta H endpoint piece is precisely this, and you can show by some parity transformation that for n minus 2 and lesser, you will have an endpoint piece which is integral over x minus horizon. So these are again light ray moments, but over x minus horizon. Okay, so basically, what was the procedure? The procedure was we used the Sarasugajin formula for these types of perturbation, and we had a general formula, and then we had a general formula for delta HA, which was this modified Sarasugajin. We studied that operator with some probe operator J and Y. It had various types of branch cuts, and in most cases, those branch cuts were easily could be dealt with. It either gave you 0 if the perturbation were fully in the Weber region, or the commutator piece if the perturbation were fully in the A region. But if it straddled the endpoint, it gave you some, you had to be a bit careful with the contour integral, and it gave you basically this lighter moment. Now, kind of aside from these technical comments, let me now go to some maybe more interesting comments for you. Is that if you, so this extended modular Hamiltonian has the property that it annihilates the state, the corresponding state. Okay, this you can show because you can show that the modular operator keeps the state invariant. So this is the expansion. This is the rewriting of the fact that H extended for the excited. That's true. Yes. Delta in general to some power acting on the state keeps it invariant. You can show it from modular theory.
Because it is constructed that way. I feel like when you this in the case of a Schottky vacuum, for instance, it's a statement that so there is some sort of a symmetry that is there. So state also.
Yeah, it definitely hints at some symmetry. I don't know what is that symmetry.
It is constructed
the way you can derive it, actually to derive it, you again have to go back to this case as if it is bipartitionable. So again, you have to write delta as rho A tensor rho A bar inverse. You can write the vacuum state, or the vacuum state in the Schmidt decomposition form. You can go to excited state. You can go to the corresponding excited rho A and rho A bars, and you can show that it is true. So delta to the IS acting on psi is psi.
Modular Hamiltonian is kind of an engineered thing. I'm not saying that it is impossible, but it's a have some problem.
Maybe the fact that I use the Schmidt decomposition, maybe that is where this is built in. It's a Reschleider type state operator. So if you write in terms of the fact that H excited, so this yields the fact that H excited acting on some psi, this is 0. And if you expand this expression to first order in epsilon, you get what I have written here. And then if you write down delta H, which is first order change in H, as the commutator piece plus the endpoint piece, then once again using the fact that H0 annihilates the vacuum state, you can show that the endpoint contribution by itself should annihilate the vacuum state. And in fact that we got those light rays and light ray moments, they actually do annihilate the vacuum state. These are shown in a paper by Kravchuk, Siemens, Duffin, and Kologlu. One interesting point is that yes. So I mean, all our calculations, we are hoping that the endpoint contribution will be there because it's some UV effect also for QFT, but for practical computations, you also have to go for conformity.
No, I'm just saying that the statement is actually there, so it's only for in the context of conformity.
Yeah, so they write down these 2-point functions. You write down the light ray operator, and they only do it for light ray operator, not for the moment. And they consider that light ray operator either on the left or on the right of a string of correlators. And then depending on whether you put it on the left or right, they could close the contour either on upper half plane or lower half plane of the x plus integral. And then there is a condition on k. The condition on, so you can expand it to, let me just do it here. So you can, so that's how they show that the light ray operator. So LK, did I write LK? Yes. They only deal with the zeroth moment of light ray moment, which is dx plus jn of this. And then they take LK in a string of, other operators. So they take L0 with some O1, O2, dot, 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 or O1, O2, dot, 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 L0. And then they show that they can close the contour, which for K, well, so for their case, it will be some other condition. But for if you take x plus to the K, you can show that if K is less than delta plus n minus 1, then you can close the contour and it gives you again 0. What I want to point out is that this is more moments than we actually need in as endpoint contribution, because our k actually goes till n minus 2. Okay, so there are actually more operators which satisfy this condition. So purely if you started trying to find some endpoint contribution purely in terms of this constraint, then you would end up with more operators than are actually present. So there was a recent paper by Belin et al. Which showed that those operators which are not present as endpoint contribution but could satisfy this condition are kind of a bad operator, in the sense that they don't satisfy a good algebraic property. So this is kind of, I find very interesting. And maybe it also tells us something about the positivity of these operators. I don't know. Yeah, so but okay, so the point I wanted to make here is that purely generally you can show that this has to be true, and kind of extending their computation, you can show that for us, for the moment, it's also true as long as k is less than delta plus n minus 1, and we are within that bound. And there are many future directions, more than I have listed here. So for most parts, I have talked about Rindlers, but what happens for finite subregions? And then we took, some space-like perturbations, but what happens if I also do time-like perturbations, in particular perturbations over some causal diamond? We are having some trouble there. You can ask that if such effects, they appear in other quantities, because this is coming from some deep algebraic property of QFT. In some fancy ways of saying it's not type 1 von Neumann algebra, but type 3 von Neumann algebra. So if such quantities are present in the total modular Hamiltonian in excited state, whether they're also present in, let's say, relative modular Hamiltonian or similar quantities, and what are their contributions in entanglement entropy and so on, or any entropy. Higher order contributions, is an important question. For example, second order is the first non-trivial order when you first of all, these types of superposition breaks down and you have mixing terms. Of course, NX type statements for stress tensor perturbation, there is a statement of positivity, which is the NX statement. But we have this higher order moments, and whether I can also have a statement for positivity statements for those operators. And finally, we actually came to study excited state modular Hamiltonian not because we thought these contributions will be there, but because we wanted to do bulk reconstruction using modular Hamiltonian for excited state. So that's a whole other business. And then we started computing these excited state modular Hamiltonians a bit carefully, and that's when we found out these results. So now it would be interesting to go back to see that if that CHEP-th has a bulk dual, then how does these endpoint contributions arise in ADS? Okay, I think that's it. Thank you. More questions? Yeah, in 2D, actually, Sarosi Ugajin did many things. They also had this connection with OPE blocks in those papers. Yeah. Yes, yes, because they don't do it, but I believe it can be, because after all, we used their formula, right? So what they do in their paper, they start from their formula, this 1/1 plus cos hyperbolic s and so on, and then they go in a slightly different way to compute in 2D these excited state modular. But they don't consider, I think, any kind of specific perturbation. It's there, yeah, it's there, it's hidden in there. What I should tell you is that we are having a lot of difficulty in considering time-like perturbation. And we see that if we naively apply Sarosi-Ugajin formula for time-like perturbation, then actually some like fundamental properties are getting violated. Like if I have a perturbation, so let's say this is my subregion, this is my x plus x minus axis, and if I have some perturbation in this causal diamond, then in some cases you can show that what is delta H. Okay, and then this delta HA should, this HA plus delta HA should give you some modular flow within this subregion. But what we are seeing is that if you consider some double commutator, and like consider its correlation functions and so on, it's actually not zero, which you would expect purely from causality. So we have, I mean, we are even contemplating the possibility that maybe Sarosi-Ugajin formula actually doesn't work in that case. Maybe there is something very peculiar with these types of time-like perturbations for which it is at all not possible to even start from as if it is a finite dimensional system and then derive Sarosi-Ugajin formula. Because remember, even deriving Sarosi-Ugajin formula, they actually, not even secretly, from the very beginning, they thought it is a finite dimensional system. I can talk about rho A and rho A bar. In fact, their formula is for delta H A. So we need some sort of formula which actually gives us delta H, I mean, without relying on those things, probably.
But I think if you take it and this value, I would think that perturbations are only allowed in the 2D.
Exactly, exactly. So I think this does not even apply.
I don't think it will.
Yeah.
There are two tensor factors.
Exactly. Yeah. So this will have effect on both sides, and